Now we are going to discuss about our fifth module. Our fifth module consists of different voltage control methods employed in inverter circuit and the working of a AC voltage controllers. First we will discuss about the voltage control in inverter. AC loads may require constant or adjustable voltage at their input terminals. An inverter is used to convert a DC voltage into AC voltage. When AC loads are fed by an inverter, it is essential that output voltage of the inverter is so controlled as to fulfill the requirement of a AC load. For example, if we are connecting an induction motor at the output of a inverter, in order to avoid magnetic saturation of the induction motor load, we have to keep the voltage to frequency ratio as a constant. So, the inverter output voltage frequency, we have to control the output voltage of the inverter, output voltage frequency of a inverter as a constant in order to avoid magnetic saturation of the induction motor. Similarly, according to the load requirement, we have to control the output voltage from the inverter. In order to obtain this voltage control in inverter, there are different methods. Different voltage control methods in inverters are external control of AC output voltage, external control of DC input voltage, internal control of inverter. External control of AC output voltage means at the output of the inverter circuit, at the output terminal of the inverter circuit, we place some external circuit to control the output from the inverter. There are two types of external control of AC output voltage, that are AC voltage control method and series inverter control method. In AC voltage control method, we are placing a AC voltage controller at the output of the inverter. The output from the inverter is fed to a AC voltage controller. The AC voltage controller will control the average output voltage of the inverter, and it is fed to the AC load. That is AC voltage control technique. In series inverter circuit, two or more inverters are connected in series according to the load requirement. Okay. That is external control of AC output voltage. We are placing a external circuit at the output of the inverter. In external control of DC input voltage, we are placing a external control circuitry at the input side of the inverter. For example, choppers, controlled rectifiers, etc. Then we are controlling the chopper in order to control the output from the inverter. By controlling the output of the chopper, we can control the output of the inverter. That is external control of DC input voltage. In these two external control methods, we need external circuitry to control the output voltage from the inverter. So, that is a main drawback. The circuit will become bulkier and the number of switches will become increased in external control of voltage source inverter. Next, third type of voltage controlling inverters are internal control of inverter. In internal control of inverter, the output voltage from the inverter can adjusted by adjusting the inverter switch itself. This is the most efficient method of control of output voltage of a inverter because it does not require any extra circuitry. The most popular internal control of inverter is pulse width modulation control. In this control, a fixed DC input voltage is given to the inverter and a controlled AC output voltage is obtained by adjusting the on and off period of the inverter switches itself. This is the most popular method of controlling the output voltage of an inverter, and this method is termed as pulse width modulation control. Pulse width modulation technique is the most popular voltage control technique in an inverter. The main advantages of pulse width modulation technique are the output voltage control with this method can be obtained without any additional component. That is the first advantage. Second advantage is with this method lower order harmonics can be eliminated or it can be minimized. But some higher order harmonics are present in this voltage control technique, but it is easy to filter out this higher order harmonics. The main disadvantage of this method is that SCRs are expensive as they must possess low turn on and turn off time. There are different PWM techniques employed in an inverter. The different PWM techniques employed in an inverters are single pulse width modulation technique, multiple PWM technique, that is multiple pulse width modulation technique. Third one is sinusoidal PWM technique, that is sinusoidal pulse width modulation technique. Third one is modified sinusoidal PWM technique, that is modified sinusoidal pulse width modulation technique. Last one is phase displacement control. Okay, first we will discuss about single pulse width modulation technique. In single pulse width modulation control, there is only one pulse per half cycle. There is only single pulse per half cycle. And the width of the pulse is varied to control the inverter output voltage. By controlling the inverter output voltage, we can vary the pulse width of the control signal. This figure shows the generation of gating signals and the output voltage of single phase full bridge inverter. The gating signals are generated by these are the gating signals. These gating signals are generated by comparing a rectangular reference signal with a triangular carrier wave. The amplitude of the triangular carrier wave is AC and the amplitude of the reference signal is AR. AR is the amplitude of the reference signal and AC is the amplitude of the carrier signal. Carrier signal is a triangular carrier signal. The frequency of the reference signal determines the fundamental frequency of output voltage. Okay, this is the output voltage. Here the figure shows the generation of gate signal for a single phase full bridge inverter. Single phase full bridge inverter consists of 4 switches Q1, Q2, Q3 and Q4. In order to obtain positive voltage, we are firing Q1 and Q2. In order to obtain negative sequence, we are firing Q3 and Q4. Okay, then we get positive sequence. When we gate Q1, Q2, we get positive output voltage. When we gate Q3 and Q4, we get negative output voltage. The gate signals are generated by comparing a reference signal of a rectangular reference signal of magnitude AR with a triangular carrier signal with the amplitude AC. Okay, the frequency of the output voltage depends upon the frequency of the rectangular signal. The ratio of amplitude of reference signal to the amplitude of the carrier signal is called the amplitude modulation index. That is, the ratio of AR to AC is the control variable and it is defined as the amplitude modulation index, or is also known as modulation index. The ratio of AR is the amplitude of the reference signal and AC is the amplitude of the carrier signal. So the ratio of AR to AC is the control variable and defined as the modulation index. That is, the modulation index, amplitude modulation index, or simply modulation index is equal to AR divided by AC. Then the RMS output voltage can be found. RMS output voltage is V0 is equal to 2 divided by 2 pi into integral pi minus delta divided by 2 into pi plus delta divided by 2 into Vs square into d omega t, the whole raised to half, where Vs is the output, Vs is the source voltage and delta is the small delta is the pulse width of the gate signal, or small delta is the pulse width of the output voltage. By varying the AR, that is amplitude of the reference signals from 0 to AC, by varying the reference signal magnitude from 0 to AC, we can vary the pulse width. Delta of the gating signal from 0 to 180 degree. From 0 to 180 degree. If AR equal to AC, the pulse width delta equal to 180 degree. If AR equal to 0 degree, pulse width is equal to 0. And the RMS output voltage V0. We can also vary the RMS output voltage V0 from 0 to Vs. By varying the amplitude of the IR, we can vary the pulse width as well as RMS output voltage from 0 to Vc. Okay. Then the Fourier series of the output voltage is given by V0 of t is equal to sigma n equal to 135 to infinity 4 Vs divided by n pi into sin n delta by 2 into sin n omega t, where n is the order of the harmonics due to the symmetry of the output voltage. Along the x-axis, the even harmonic, that is n equal to 2, 4, 6, 8, etc. are absent. Only odd harmonics are present in the output voltage. Next, this figure shows the harmonic profile with the variation of modulation index m. With variation of modulus, this is the modulation index. By variation in the modulation index, how the harmonic profile varies. df is the distortion factor. From this figure, we can say that the dominant harmonic is the third harmonic. The dominant harmonic is the third harmonics, and the distortion factor increases significantly at a low output voltage. From this harmonic profile, we can say that the third harmonic is dominant. Okay, this is single pulse width modulation. In single pulse width modulation, a single pulse is present per half cycle. We can produce this single pulse by comparing a rectangular wave with a rectangular reference signal with a triangular carrier signal, and the ratio of AR to AC is